Good evening. Tonight we welcome Colin Steele, an amateur astronomer with professional experience who enjoys giving talks on a wide variety of astronomical topics, inspired by the early events of including Apollo moon landings. He studied mathematics and astronomy and astrophysics at St Andrews University, and then he got a PhD in applied mathematics on the topic of the dynamics of solar prominences. He's now teaching mathematics to students in many parts of the University of Manchester, and a former member of the Dundee Astronomical Society is now dwelling in Dore, Sheffield, and a member of that neighbouring society. Thank you very much.
Yes, thank you. Thank you, Roy, Paul. Now, I'm told I need to press the button on the microphone. I have done so. I'm hoping I've pressed it an odd number of times. You've not got the lights on. We don't have the lights on.
We've got the lights on.
Okay. Thank you. So I've called this one Astronomy in Flatland. So what do I mean by this? All being well, I will show you many astronomical phenomena, but all slightly different. So let's get into it, and we go back, what, 140 years to a book that was published, Flatland, or Romance of Many Dimensions. Now, I'm not really sure about the romance bit, but this was maybe the kind of language that was used at the time, and we see the author, Edwin A. Abbott. Now, some of you may know what the A stood for his middle name. Some of you can speculate, but I'll try and come back to this point. This was the original cover that we see, and this is Abbott himself. He published this book, and we can see, well, I've given away what his middle name was. Edwin Abbott Abbott. And it would seem that some of the other kids that were at school with him took this as an opportunity to bully and whatever else, to mock him and so on. The fact that his middle name was the same as his surname. So they would call him Abbott Squared. Now, this must have stuck with him, because in the book here, Flatland, the hero of Flatland is A squared. So, was it written with a kind of personal view in mind? Now, A squared, let's give him just a few features, but you can see, well, the main characteristic of A square was that he was square. And in the book, he was a professional man. It's not quite mentioned just which profession it was he was into, but a professional man here. But we also meet other inhabitants of Flatland. Flatland is the country, the world, the universe that they inhabit, and it consists of two dimensions. In Flatland, we have north-south, we have east-west, but we don't have up-down. Now, we will see variations on this, and we will see some of the restrictions that it causes. But other inhabitants of Flatland, this equilateral triangle, a tradesman of the respectable class. Why does he have to feel he has to add the of the respectable class? Is it not the case that all tradesmen are tradesmen of the respectable class? Well, maybe that wasn't the case in 1885 and so on. a gentleman, a pentagon with 5 sides, a nobleman, an octagon with 8 sides. And it seems that the higher your status, the higher your rank in society, the more sides you have. And it seems, well, it's not a king that's in charge, it's a priest who is a circle, or maybe who has a very large number of sides, so many that we can't actually see that. Now, any more inhabitants of Flatland? Yes, the more sides, the higher the position. And also, as history goes on, each son has 1 side more than his father. So we see A square's father, the equilateral triangle, and there's a brief mention of his son. He's got a few sons and a couple of grandsons who are hexagons. Okay, that's fine. But what about his grandfather? Who would have been the father of the equilateral triangle? Well, it turns out that the father of the equilateral triangle was a triangle with an angle of 59 degrees, and his father was 58 degrees, and so on. I mean, this looks a bit strange, but more strange is to come. We can see the workman is more pointed, and it turns out the more pointed you are here, the lower your position is in society. Now, at this point, I'm probably, it doesn't look particularly politically correct, or even common sense correct. But there is worse to come. And it's not the irregulars, but the irregulars were shapes that just didn't fit any pattern. They might have had, as we can see with the green one, an angle pointing the wrong way, or different sized angles. Now, one of the chapters in this book goes into interminable detail about if you're out and about and you encounter various shapes, you can tell from the way that the light is reflected just what kind of a shape this is. And it all works very well, but it would not work for the irregulars. And sadly, they were ostracized from society. They were locked up in various prisons and asylums. Now, often you wonder, what was Abbott trying to get at here? And, it may be what he was trying to do was to draw attention to how ridiculous some of the norms of Victorian society were. That those are people who needed our help rather than to be locked up. But this is where they were in the book. And the other issue here, well, don't shoot the messenger. There is a distinct disparity between the men and the women in Flatland. The women are straight lines. And believe it or not, yes, he does mention the danger of if you're out and about and a woman bumps into you, that it's a very sharp point and the consequences there. As I say, don't shoot the messenger. This is what Abbott mentioned here. Now, the first half of the book is just some generalities about the society there. And then he goes into a tale that happened on New Year's Eve. And we see that A square was in the main room in his house. The houses were all pentagons, and rain came from the north. Remember, there's no up or down. Rain would come from the north, and the roof here would deflect the rain, prevent it from coming in. But he's in the main hall. We can see his wife, his various children and grandchildren. And then the slightly worrying thing, look at the shape he's drawn the policeman. So was he an anarchist or something as well as everything else? But here we have A Square in his house, and later on, yes, his wife went to bed and he was feeling a bit restless. He detected a presence, and then suddenly the circle had appeared in his house. And he had various reactions to this. How has this being got in? Is this a circle, a priest that has somehow come here? And the circle got bigger and bigger, bigger than him, and then smaller. But then they started a conversation. So A Square is in red, the circle is in the kind of yellowish color. Where do you come from? From space, sir. Where else? And you can see he's being quite polite to him. Pardon me, my lord, but is not your lordship already in space, length and breadth infinitely prolonged? But we can see here that this new being is trying to educate A Square that there is more to life than just the 2 dimensions he knows. And they have a bit of a misunderstanding, but 3 dimensions. Would your lordship indicate or explain to me in what direction is a 3rd dimension unknown to me? So then, this circle is actually a sphere inhabiting 3-dimensional space, but of course, if it's coming through the plane of Flatland, it comes as a circle, and then the sphere takes A Square out of his world and shows him some of the things in Spaceland, 3 dimensions. Of course, we live in a 3-dimensional universe. We cannot perceive, unless we think in very strange terms, we cannot perceive of a 4th dimension, but in the same way, A Square cannot perceive of a 3rd. But he's taken up out of his experience, and he's able for the first time to look at his house from the upward direction. And he sees all sorts of things going on there. And eventually, yes, he comes back and he tries to tell everybody else in Flatland about his experiences. Bad move. There is one more patient in the asylum at the end of it all. So it's a little bit depressing at the end there. But, well, what's this got to do with astronomy? There's not much of a way to put astronomy into this Flatland, but other people have suggested 2-dimensional universes. 1907, Hinton, he thought of a planet that he called Astrea, and here we have east and west and up and down. So you've got your planet is actually a circle. People live on the rim of the circle. You could think in terms of a coin or something. And, well, let's see some of the inhabitants of this 2-dimensional world. Yes, here we have a man in this 2-dimensional world, and here we have a woman. Now, there's a bit more equality there. The man is slightly bigger than the woman here. But think of this diagram. 2 men, a man and his son, and if they want to face each other, he's got to turn them upside down. Now here we have the geography of Astrea. There were 2 areas that were inhabited, Scythia and Eunaea. We can see the Black Sea, the White Sea, forest, desert, mountains. And the Scythians, we are told, are barbaric and uncultured, whereas the Ionians are civilized and cultured. Now we can probably guess which of the two groups put forward those descriptions. But as often is the case when you have two groups, what happens is they have a big fight. And we can see now the Scythians and the Ionians, remember that in 2 dimensions they cannot turn. What's happening here is it seems the Scythians, the barbaric and uncultured people, are at an advantage here, because let's be quite honest, if he's going to wave this knife, this sword about, we can guess who he might do more damage with just poking about behind his back. Although it did occur to me that maybe a curved pea shooter might be the weapon of choice here. That might do a bit more damage. But they had another plan there. What they would do would be to leave some of their number behind to try and defend things, and others would travel across the White Sea. They would climb every mountain, go across the desert, climb every tree in the forest, take a boat across the Black Sea, and having done that, sneaking up behind the Ionians and claiming victory would be easy to, because now they would have the advantage of direction there. Well, that was a bit of fun in the book. There's still not much astronomy there, but we can put in astronomy there, because you can see it's a world and there's areas that are not in the world. So we have this world, a circle, and this circle could be accompanied by other objects in the universe. Now, there's a few things that we need to think about, and one of those is gravity. How will gravity work? Yes, it'll pull things in towards each object, but you see in our universe, we have an inverse square law for gravity. Now, I'm not going to put in, or I'm not going to show the pictures with lots of equations on them, but we can see here that you've got that the force of gravity, it depends on the masses of the two objects, but it also depends how far apart they are. It's an inverse square force. Move the objects twice as far apart, gravity goes down by a factor of 4. But what would happen in Flatland? Well, you would just have an inverse force. We can think of gravity spreading out over a sphere, but they would just have gravity spreading out over a circle in Flatland, so you would have an inverse force. Now, one thing this does, it makes the equations rather more difficult to solve. Isaac Newton was able to solve the equation of gravity and show that Kepler's laws were the result of that. But if you have this inverse force, it's going to be much more difficult. In our world, Isaac Newton had to invent calculus to solve the equations. To solve the equations you get out of this, he would have had to invent calculus and the computer. So that was well ahead of his time. You can do some calculations involving integrals and conservation of energy, and you find that, yes, if you have planets going around the sun, They cannot fall into the sun. They cannot go off to infinity. But solving the equations is a little bit trickier, and we do need the computer on that. Now you can have, if we look at the middle diagram, we can see if you project an object around a star with exactly the right amount of velocity, it will go round in a circle. But if it has a little bit less than that on the left, or a little bit more velocity, as in on the right, then it turns out that it has a different shape of orbit from what we're used to, and in particular, although it goes in to a particular distance and out to another particular distance, the orbit does not join up. And indeed, we can try to show what we've got here. You can see, yes, we've got an object, a planet, going around the sun, gets closer, gets further away. You can see that, well, I can kid myself that when it gets closer to the sun, it's moving more quickly. Maybe I am kidding myself, but I've seen more extreme cases where that's more obvious. But yes, you can have, in 2 dimensions, planets going around the sun. And they're not in elliptical orbits, but they do have the feature of the ellipse that they are closer to the sun, something like now, than other times like now. So we do here have, yes, a planet going around the sun. Okay, now it might be that you've got circular orbits, in which case, let's equate the gravitational force and the centripetal force, and we end up with the velocity of an object in its orbit is independent of the size of the orbit. And in fact, Kepler's third law, we are used to, yes, the period being proportional to the size of the orbit to the power 3/2. In Flatland, it's simply a case of the velocity, that the period is proportional to the size of the orbit, and the velocity is constant across all the planets. We are aware Mercury goes much faster than Pluto in its orbit, but they'd all be the same in a 2-dimensional universe. Okay, what about things like seasons when you're on an orbit here? Now, one thing we can see is we look at an orbit here, and yes, we've got, well, a couple of, well, how many orbits is this? It's hard to define here. What is a year here in Flatland? Because you can see that during the time it takes us to go once around the sun, just ending up about here, it's, we've gone in, out, and started on the way in again. So we've possibly got different types of year. Sidereal year. We go once around the sun, so that we're between the sun and the same star. That would be a sidereal year, but we could also look at the anomalistic year. Far point to far point, or perhaps near point to near point. Different types of year. The year that we have is neither of those. the year that we design our calendar on is called the tropical year, and that's all about the interval between points such as where does the sun cross the equator? In March, the sun will cross the equator from south to north. That's what the seasons are based around, so we stick with that. But there's no equator, there's no south to north, there's nothing like that, so we don't really have our type of year. Now let's just examine seasons in our universe. Why do we have seasons? Well, the main reason that we have seasons is the tilt of the Earth's axis. At the moment, the northern hemisphere is tilted away from the sun. And in fact, in a week or two, it'll reach the sun will appear at its furthest south because of the orientation of things. So it is winter here, or at least winter will start, whereas summer will be starting in the southern hemisphere. And that is the main cause of the seasons. But we do have another two causes of the seasons. The Earth, believe it or not, is closer to the sun in January than it is in July. So that tends to make the southern hemisphere seasons more extreme. We also have more than half of the land in the world is in the northern hemisphere. A lot of what's in the southern hemisphere is water, so this tends to regulate the temperatures. So that would make the northern hemisphere seasons more extreme. Those second and third points really are secondary causes of the seasons, and they cancel each other out. But if we look at what would happen in a two-dimensional world, in a flatland, then this tilt is a three-dimensional effect, as is the northern and southern hemispheres. So we're left just with the planet closer to the sun at some times than at others. So we can have seasons, but unless the orbit is a more eccentric one, it's going to be a case of they might not be particularly significant. Now, what else do we have? Earth around the sun, seasons. Next object, moon. What would we see if we were to look at the moon? Now, we've made an assumption there. Our planet will have a moon. There's no real reason why it couldn't. Of course, it's all fiction anyway. But there's no real reason, there's no inconsistency there. It may have several moons. We're the only planet with one moon in our solar system. We will discover others in due course, but I digress here. Let's imagine, we've got the moon going around the Earth. Will the moon show phases? What will the moon look like in the sky? Or for that, yes, what will the sky look like? If you imagine we have an astronomer looking at the sky, we don't have north or south, east, overhead, west. We've got just a line for the sky, and the moon will take up part of that line. Now let's imagine we're observing the moon at this point. The part towards the right here is in darkness and we won't see it. The part on the left, which will be most of what the line that we see for the moon, that will be lit up. So what we wouldn't have the crescent or the half moon or anything like that. Instead, we would have the moon giving lines of various lengths. at different times. So just after new moon, you can see that from the Earth, we would only see a little bit of the moon towards the right. Close to first quarter, we see half of the line lit up. Maybe that could be a half moon. Instead of a gibbous, it's most of the moon. And then the same in the waning phase of the month there. Now, you might also have that the moon's orbit could be eccentric, and the moon could start to appear larger or smaller in the sky, as well as the phase having an effect here. But what happens at new moon and full moon? What happens at new moon in our universe? The moon will pass near to the sun, and we might have the moon passing to the north of the sun. We might have the moon passing to the south of the sun. And very occasionally, the moon will pass directly in front of the sun, and we'll get an eclipse. And we all go, well, not all of us, but we all either go or would like to go off to other parts of the world to see the eclipse. But in Flatland, we can't have the moon passing to the north or to the south of the sun, and we're left with the conclusion that every month the moon will pass directly in front of the sun. Of course, we're dependent on geometry. It's a remarkable coincidence that the angular sizes of the sun and the moon are so close in the sky, and that the distance that the moon is from the Earth causes the moon sometimes to appear bigger in the sky than the sun, sometimes smaller, causing total or annular eclipses. We really don't know, I mean, the relative sizes of the sun and the moon, but every month the moon would give us either an annular or a total eclipse. When it's annular, of course, I don't mean the ring, I just mean a glowing part either side, and we don't see the bit in the middle. So every new moon will see an eclipse, and yes, we don't necessarily make the assumption that the umbra will reach the Earth, but it could well do so. But you'll see a total eclipse if the umbra does, an annular eclipse if it doesn't, and then you've got the partial eclipse before or after. But yes, if you have the annular eclipse, you can see the two parts of the line, and it's incomplete in between. But what about at full moon? What's going to happen at full moon? By the same token, we are going to have an eclipse of the moon every month. And remember, if we have several moons, this adds to the situation. Again, we can't make too many assumptions about the geometry. It might be that there's room for the moon within the Earth's umbra. It might be that, well, before or after, we'd get the partial or the penumbral eclipse, but then we might have the situation that you had an annular eclipse of the moon. And it's nothing to do with being in Flatland, it's just due to the relative sizes of the various objects here. And of course, moon further away, you don't get a total eclipse. You would just get a penumbral eclipse. So new moon, eclipse of the sun, full moon, eclipse of the moon. What about planets? I assume we'll have planets. If our planet can go around the sun, why can't other planets? you get an awful lot more occultations. Now, one of the great things about Flatland is you can represent it on a two-dimensional screen. Whereas, in 3 dimensions, we're always having to consider viewpoints and things. But let's imagine we have a planet and some moons, and they're going to pass in front of a star. What do we see? Every moon will interrupt the light from the star. The planet will interrupt it for a bit longer, but we'd end up with a situation there that we could draw a graph showing the amount of light getting through at various times, and because of this large number of occultations, it would be much easier to discover moons of the planets, asteroids, distant planets, and so on. The great history of the discovery of the outer planets might just not have occurred in a two-dimensional universe, because we'd be discovering them every time they passed in front of a star. Or a planet with rings. You can see that when the ring edge on blocks the light, and we'll assume that some light can get through when you've got it not being edge on, but you end up, when you've got a planet with several rings, you'd end up with a light curve looking like what we have here, something very distinctive here. So again, the fact that the rings of Uranus were discovered but almost 200 years after the planet itself, chances are that would not have occurred in 2 dimensions. Binary stars. Well, it'd all be eclipsing binaries. They might have a long period, and we might not know that they're going to eclipse, but watch them long enough, and they will. We can see here, well, the concept of viewing the eclipsing binary, it looks very much like what happens in our universe. You've got the main minimum there, a secondary minimum at the opposite point on the light curve. Yes, you're able to see the amount of light change there. So the bottom line for all this is occultations are much more common in 2 dimensions. They just can't miss. Once they come together, one will pass in front of the other. Okay, stars. What do we say first? Constellations, or maybe this is just an excuse for me to show a few pictures of constellations. Here we have, for example, well-known, well, it's an asterism rather than a constellation. It's part of the Great Bear, but we have the plough here. People thought this had the pattern of a plough, and I can see where people were coming from. You've got Orion here. People could speculate that this represented a figure out hunting. Or we've got Gemini, Castor and Pollux on the left. I think it's Mars, the interloper there, M35 over towards the upper right, and so on. They reckoned they could make legends about a pair of twins that are represented here. Or Cassiopeia, a lady strapped in a chair. Well, some of them we can go along with, perhaps more than others. A lion here. Somebody riding in a chariot. I have to confess that probably, yes, the banner Our Constellations has gone over Capella and the kids here, but you can see some of the, you can see Menkarlina towards the left and so on. So those are our constellations. In Flatland, a constellation would look something like this. The sky would just be a linear band, and we have dots along it. So what is this? What would we make of this? And we can't call all the constellations the series of dots, but, well, maybe the Flatlanders would have something that this reminded them of. Let's move a bit further away from the stars. Galaxies. How would galaxies appear in Flatland? Well, in a sense, you'd be talking about everything. You'd be observing edge on. And the chances are that, you'd miss it. You wouldn't see any beautiful spiral structure. You'd miss out on that. You'd have to infer the structure from the light curve rather than anything else, which is a bit of a disappointment here. But if there were spiral galaxies, we wouldn't really see that. The people there would end up from a light curve such as the one here. Or if you have elliptical galaxies, a more regular light curve, or irregular galaxies, an irregular light curve, not much of a pattern to it. But of course, there could be other types. We really don't know. Okay, another phenomenon, aurora. Now, the problem is, aurora depend on magnetic field. Many of the manifestations of magnetic field depend on there being 3 dimensions. So kind of fudge this a little bit here. Magnetic fields, that's a 3-dimensional phenomenon, but let's pretend it's okay and we can have aurora. If somehow we think in terms of it being some kind of a property of space, we're used to, you've got the magnetic field going, say, upwards here, you've got a current in the wire going left to right. If I've got my vector products correct, then the wire would experience a force to take it out of the screen and towards you. But somehow, if we say it's a property of space rather than having a direction, I'm fudging it really. But what would it mean? If we have, here we have an observer on the left. That rectangle was supposed to be all the way along. It's not as if it's supposed to be on someone's roof, but we've got an aurora, red and green. Well, we don't know that to be red and green. We don't know the chemistry of it all. We don't know the, whether we'd have the same phenomenon of colors, but let's not let such things get in the way. But if there was a city, either the city would be ahead of us or behind us. So what we'd actually end up seeing, you'd have maybe the red light pollution of the city. I know it's something that we're all used to here, the light pollution of the city getting in the way of astronomical objects, but you could never position yourself so that you didn't have a city either close or far away in exactly that direction. So sometimes the geometry gets in the way a bit here. Meteors. Yes, let's assume we have meteors here, particles entering the atmosphere, burning up, and here, from the Earth, we can see, let's imagine we have a shower of meteors. They're in green, they're coming out from the radiant that you can see in the center, and we've got a couple of sporadic meteors. Those sporadic meteors are clearly not shower meteors. They're going in the wrong direction. But in 2 dimensions, where the sky remember, is a line, we would actually see, if we've got a radiant where I've drawn the arrow, you can see the shower meteors, either they're going up from the radiant or they're coming down from the radiant. What of the sporadic meteors? If they were just in any random direction, it's almost a 50-50. Are they going towards the radiant or away from the radiant? Okay, there is one that's going across the radiant here. So the bottom two sporadic meteors would clearly be sporadic ones. But this red one up at the top, who is to say that that is not a shower meteor? They would not be different colours. That's just for distinguishing purposes. But you can see you'd have to have extra factors in your calculations about sporadic meteors for how many actual shower meteors you had. But how do we observe everything? What would a telescope look like? Well, before we go into telescopes, let's consider something a bit more fundamental, a house. So here we have a house in Flatland. Okay, it's a rather simple one, just consisting of the one room. We've got a door that you can see in green, and the inhabitant comes up to open the door to go into the house, does indeed open the door. What happens next? I can just imagine the parents in Flatland. Don't leave the door open, the roof's going to fall down. I'm sure we've all at one point been scolded about banging the door too much, that it's going to bring the house down, but perhaps it is a more serious issue there. Well, what can we do to make our house a bit more sturdy? We've always got the brute force possibility. Just strengthen all the joints, use heavier material, and so on. Or we can try various other things. We can have a semi-detached house here. And each house is actually balancing the other. So there'll probably be a fair amount of stress at the junction here, but you could open one door and it wouldn't be totally unbalanced. Or you could have an airlock system where you've got two doors, open one, go into the porch, open the other door, and there you are. So that's some of the things that we need to think about when we're building any type of object. So let's try and work with telescopes. And if we start off with the simplest type of telescope, the refractor, then yes, we could have something like this. But as you can see, I've written there, what's holding up the top part? It's the optics there. Now, you don't want your optics also sustaining the force of the top there. We could forget about the top and hope that things were going to work. Or maybe we consider the reflecting telescope. Well, what will we do here? Well, you can see the problem is that when you've got the light entering, say, a Newtonian reflector, bouncing back, being deflected to the side, we've lost half the light here. Now, I know in a Newtonian reflector, we do lose about 10% of the light through the mirror. It depends on the geometry of what we've got. And we've also got the situation here that this bit is being held up by the eyepiece. This doesn't sound a particularly good idea. The eyepiece is probably one of the more delicate parts of a telescope, and we might want to change the eyepiece anyway. So it doesn't look a particularly good way to do things. What can we try instead? We could try putting, I suppose, a plate, a glass plate, a transparent plate across to hold up the flat. We've still got some problems about the end of the telescope there, but perhaps slightly less. Or we could decide, well, actually, we'll have the flat at the side here, just at the mouth of the eyepiece, and this takes us a bit back towards the Herschelian telescope, which was built along those lines. Or we could try something Cassegrain. Okay, some of the issues about building a telescope. What are we going to put the telescope on? Now let's imagine we have something like this. Our telescope can point, down low towards the left. Probably wouldn't want to go all the way to the horizon, but yeah, that looks fine. Or we can tilt it back, higher up still, but this is as far as we go. We can't get past that point. So what can we do? We can't view anything over towards the right. You could have two of them, but I suppose, well, it costs twice as much, and isn't one telescope good enough for you? There's all sorts of issues there. There are other things we could try. Mount it on the side. We can point it to the right, we can point it overhead, and we can point it to the left. Okay, that's looking quite good, but of course it would tend to slide down. Maybe we need a counterweight. There's all sorts of possibilities there. Now, what about a dome? Keep your telescope inside the dome. Let's put the dome here. Well, it's not easy to remove. If you need to somehow get this dome over the top of your telescope, then, it's not really a dome if it's something that needs to be removed each time. If you do have a gap, how on earth do we move the gap here? It's not just a case of turning the dome. There are suggestions involving having a big circle with a gap and then the telescope is floating on something inside, but something suggests to me that this isn't going to work. But then it's the humble runoff shed. We can have a situation like this, and we take our shed, and when we want to observe, just pull it off, and in fact, it might even be a runoff and fold up shed. Okay, sounds fine so far. And sometimes the physical problems are the easiest ones to solve. But what's going on here? We've got our astronomer at the telescope here. We've got other people there. Now, those people, who are they? Are they people waiting to use the telescope? As, probably this would be a sign of a very advanced society. But the chances are they are people that just wanting to get past, and this telescope is in the way. They need to climb over the telescope. Well, that's a human problem, or an alien problem, a Flatlander problem. I will make no attempt to solve this kind of thing. If we have a radio telescope, then you can see we've got some of the same problems here. That what's supporting the top bit here? If you've got a wire from your detector through to the electronics, then how's the top supported? Maybe you could have something like this. You have the electronics there, and they just store until you complete the observations, and then you put another wire through the hole, and you are able to access the results there. So you can't get the results during the experiment, but you can get them later. Or, and we're back to the same principle as the Herschelian, just forget about the top. Okay, that's a bit about telescopes there. Let's get back to a square. When a square has been through his adventure and he's paid the price to society for telling everyone about it, he does get speculating, and we see in the book about some other trips. So where else could he go? His next journey, he went to Lineland. He went to a one-dimensional universe. And he saw himself as trying to convince all the people in this one-dimensional universe that there could be a two-dimensional universe. So he'd swapped roles now, really. He was playing the role of the sphere, although he was a square. But what did he find in Lineland? Here we have Lineland, and the most important being is the king of Lineland. And you can see that there's other inhabitants. The men are near the king, boys next, and women on the outside. And apparently there are certain functions that are carried out by sound. But enough of that. What about some astronomy here? Well, in Lineland, if everything is in a line, you just have the sky is a single point. You could have the sun, you could have the earth, but the earth has nowhere to go except towards the sun or away from the sun. The gravitational force from the sun will pull the earth towards it. The earth will fall into the sun. We can do some equations involving quadratics, and it's inevitable the earth will fall into the sun. The only thing is, well, maybe gravity is quite weak there. Maybe it'll take a long time. But quite early, the people of Lineland would have an idea about how long the universe was going to last. Okay, back to the sun and the earth. Some astronomers, well, you could have a solar astronomer at one end and a stellar astronomer at the other end, who would only be able to see one star. And to complicate things, if you had a moon, you would have at one end a constant occultation, and at the other end you would have a constant eclipse. You'd also have issues about would the sun warm the earth and so on. So we're getting a bit back to the physics of that now, but a square had an interaction with the king of Lineland. And then he went on another journey. So he'd gone from Flatland to Lineland. Where did he go next? You've got it. Pointland. There's Pointland. No dimensions. It's just a single point. And he met the king of Pointland. And, okay, the king was very happy, although he was the only thing in his universe. And, well, there's not really much astronomy to talk about. So let's replace this journey with a different journey that was not in the book. when A square went to a 4-dimensional universe. Gravity would be inverse Q. So let's see what happens if we model orbits in 4 dimensions. Now, if you project an object around the sun with exactly the right speed, it's going to make a circle, and then it'll make another circle, and so on. Let's see what happens if we give it slightly less than the critical speed. You can see it's going around the sun. It looks like a circle, but it's actually slightly inside. And it's going further and further inside. And you can actually, you can work with the algebra on this, on the inverse cube force, and you can see, yes, it's a matter of time before the planet falls into the sun. And then, if you give it slightly more, it looks like a circle. Oh, that's the same one again. It's gone back inside. But if we give it slightly more than the critical velocity here, it looks as if it's going around in a circle, but it's actually slightly outside, and it's getting more and more outside, and eventually this one will go off to infinity. So if you're trying to model it in 4 dimensions, unless you have exactly the right speed, the planets are either all going to fall into the sun or they're going to go off to infinity. And then working with exactly the right speed, it just needs the slightest perturbation to upset that. So an additional planet would destroy the first planet. Either it would cause it to go out to infinity or into the sun. So you couldn't really have much of a situation in 4 dimensions. Okay, so what do we have here? 2 dimensions. The planets remain in orbit. The orbits don't join up. Some phenomena are changed, enhanced, removed, particularly something like eclipses and occultations. Those are more common. And you need to modify the observing equipment. 1 dimensions, the planets will fall into the stars. 4 dimensions, the planets will go off to infinity or fall into the stars. So I conclude, well, perhaps we do have the richest astronomy, the richest universe here in 3 dimensions, but maybe 2 dimensions runs it a little bit close. So we've got, other than 3 dimensions, yes, it's 2 dimensions that are the most interesting case. Okay, it's a bit of fun, it's a bit of fantasy. We did see a lot of astronomical phenomena, but so if you're looking for how do I help, what's the best way to focus my eyepiece? Yes, the talk hasn't said much about that, but hopefully it's given you a few things to think about. Thank you.
Colin, thank you very much.
It's always a pleasure to come.
I always thought that dealing in 2 dimensions would be easier.
Well, I don't show the maths of
it. But obviously not. Ladies and gentlemen, we're into questions and answers. As usual, those people online, if you would put a digital hand up, those people in the room, just attract my or Roy's attention, and we'll take it from there. So, Roy, a question.
Yeah, thanks, Colin, for an interesting talk. It just occurred to me while you were talking about 2D, 1D, and point that in our universe, the light from a star falls down, reduced to like inverse square. So 2D, it would be inverse to R, the same as the gravity. But on the line land, it wouldn't decrease at all. So the sun will be as bright as a star.
That's true, yes. Yes. If you've got a star on one side, the sun on the other, the sun would be closer. Or maybe it wouldn't need to be that close, because it would warm the very limited surface of the planet. Yes, as you go further away, then yes, I've not thought of that one before. That's a very interesting development.
The star would be as hot as the sun as well.
Yes. Yes. Yes, we're going off to get some heat. We're going out at night.
I'm looking around for other questions or comments. Nothing online. Tony Morris in the room.
Hi, Colin. You said when we drop from 3 dimensions to 2 dimensions, the equation's more difficult to solve. Is this why when these cosmologists and string people talk of n equals 8 and all this, is that why they're talking about those numbers? Because they can solve those equations, but they can't solve n equals 4 or what?
Ah, yes. And when in essence, whether it's 2 dimensions, 3, 4, 5, or whatever, if it's 3 or more, that's one thing. But you're dealing with polynomials. But at some point, if you're dealing with an inverse force, you've got a 1 over r term, and if you integrate that, you get a log. So you've got equations where you've got a log kicking around in your polynomials, and you're not going to get a good solution to that. So the 2-dimensional situation is different. It is more difficult for a reason that doesn't really affect the other ones.
Okay.
But yes, you can just deal with polynomials and solve them. But when you've got a log kicking around, that's a problem.
But it's a limitation of mathematics, isn't it?
Well, yes. As I say, the Flatland equivalent of Isaac Newton would need a computer as well as his calculus.
I'm looking around for any other questions or comments. Your 2-dimensional, your Flatland telescope, would we know that as a meridian telescope?
Oh, in a sense. In a sense, yes. You've got, I suppose, the principle of the mount, in that I think in terms of, you've got east-west, but it's not much of a difference to then being north-south. You would have a very limited sky that you can observe with it. So some of the mechanics would be quite similar there.
Yep.
Because the stars never actually change. So you're not waiting for anything to change. It's the same stars in the same place all the time.
Would your planet be rotating?
I would assume that it would be rotating. You might just get very slow rotation, but you certainly have nothing crossing your plane.
No. Yeah. So it would be, it's just the thought of that makes it really interesting, because your orbital period and your year would have a direct effect. Your orbital,
I mean, you could, well, depends on the relative values. You could have the kind of situation on Mercury and Venus that the day being longer than the year.
Yeah.
Again, it just depends on the numbers that we have there.
I'm definitely sticking to 3 dimensions.
I don't know if you've got much choice on that.
Right.
Sorry, I've just had another silly thought. You're on about your telescope with the people having to wait to cross over. And I thought you could actually build a tunnel with airlocks, because you'd have to support the land, else it would crush them as they're going down the.
Well, that's true. Yes, yes. Tunnels would be something of a challenge because, as you say, you would have to make sure that there were enough, I suppose, doors, airlocks.
Have to be airlock, because you couldn't put bits off, because you couldn't get past them.
Yes. Yeah. I mean, although, maybe they'll pass a law to say that astronomy gets priority. Yes, it is. And the rest of what I've mentioned is.
Yes, Tony.
Tony Hood in the room.
Thank you. Where would time figure in all these dimensions?
Oh, yes. I mean, I'm assuming we are talking spatial dimensions. So you've got those dimensions and you've got time. I mean, once you get into the kind of relativistic quantum side of things, yes, I know people have speculated that perhaps somewhere in our universe, yes, you've got 9 dimensions or 23, and that space and time get a bit blurred. I don't know a great deal about this, but I'm kind of working in a more classical situation there, that we have distinct dimensions of space and time. Of course, sometimes I think in terms of the second dimension of time. What would have happened if that's along the second dimension of time? If Galileo had realized that this star that he thought had moved from one night to another, if he'd gone back and checked, where would we be? He saw the planet Neptune, he saw it move. He just casually wrote down it seemed to be in a different position last night. And if he'd just gone back and followed up on that, where would history have been? Second dimension of time, what if?
You could waste a lot of time.
You could, yes. You could waste a lot of the first dimension of time.
So that is definitely an internet rabbit hole. You don't want to be going down there. I'm still looking for questions. I think that's it. Colin, thank you very much. I think you've given us lots to go and worry about that we didn't have before, but thank you very much for giving us the opportunity for that. Ladies and gentlemen, will you join me in giving Colin Steele a huge Max Princeton Astronomical Society? Thank you. Thank you very much, Colin.
No, it's always good to come. Thank you.